Hi, folks. Welcome. And what I want to do here is I would like to go ahead and pick up where we left off. Hopefully, this will be the only video that you'll have to see. So, if you would, please turn to, I believe it is page 15, 14 or 15 in the notes. So what we're going to do here is we're going to find the p-value for a two-tailed hypothesis test with a test statistic of, and let's pick a negative value here. Let's do z equal to negative 2.091. Okay, so what we're going to do here is basically figure out what the p-value for this will be. So believe it or not, that's actually a very easy thing to do here. So in order to do that, all you really have to do is you literally would draw a picture. And if it's a two-tailed test, your z value or your standardized test statistic could be positive or negative. So we're going to figure out this area here, but we're also going to basically figure out the positive side area. But these two areas that are shaded happen to be the same thing. So basically, you can do 2 times normal CDF from negative 10 to negative 2.091, 0 and 1, or you could do twice this area. So if we go about doing that using our wonderful calculator here, oh, that should be negative 2.091. So good thing we caught that here. And we get 0.0365. And since this p-value is lower than alpha, we would be rejecting the null in this instance. We would wind up rejecting the null as kind of expected here. So one thing we'll do here also is we're going to do the critical value test. So the reason we do the critical value test, it's kind of a throwback to ask your parents or grandparents that took statistics. Now, you want to look for alpha equal to 0.05, and you want it to be two-tailed. And since you want that to be two-tailed, you look at this sheet here, and since it's two tails of 0.05, and we're still on large degrees of freedom, it's going to be 1.96. So basically, it would be positive 1.96 or negative 1.96. Now, these regions, which I will shade in red, are known as the rejection regions. It can be rejected if it's here or if it's here. Now, the z value that I gave you was negative 2.091, and that follows right here. So that gives us just the same kind of evidence that we would be rejecting the null hypothesis. And I'm sorry, I did not mean for that to be t. That should have been a z. So there's that. So yeah, because if p is low, you reject the null. Now, let's do a right-tailed test where z will be 1.874. So since this is a right-tailed test, all you have to do is figure out this area of 1.874 on. And you would just simply normal CDF that yet again. Oh, not inverse norm. So we'll normal CDF this 1.874 to 10. And since we're dealing with the standard normal distribution, mean and standard deviation are going to be 0 and 1. And this is going to be 0.0305. So that area is going to be that. So in that case, we would reject the null. Now, the other reason we find the critical value is simple. Basically, the reason we'll find the critical value is because that's going to connect it directly to your confidence intervals. So here's what you're going to do. So if we want this area in the right to be 0.05, this whole area is going to be known as the reject region. And so we're back to area in one tail of 0.05, and looking at large degrees of freedom, it's going to be 1.645. So your critical Z is 1.645. Now, the Z value that I gave you to work with was 1.874, which was inside of here. So that's why we rejected the null. Now, in the first example that we did, we failed to reject the null because the p-value was higher than the alpha given, even though that p-value is actually the lowest in this first example, the alpha threshold was much lower. So, and considering the fact that the critical value was where it was and our Z value was here, now what we did in the previous class was we chose an arbitrary Z value, and that was definitely going to be in the rejection region, and we saw that, yeah, that's rejection territory. So that's what we do with that. Now, we're going to go ahead and carry out the hypothesis test in of itself. Now, the Z-test for a sample mean can be used when a sample is random and the population is normally distributed. But here's the things. The conditions are simply implied. In other words, you don't really need to verify them. We're going to do kind of an exploration at another time. What happens when conditions are not necessarily held? So this is kind of the process here for a hypothesis test. You state the claim mathematically. In other words, your null and alternative hypothesis, your level of significance, which is given to you, your standardized test statistic, which is Z. This should look oddly familiar to you. And it's central limit theorem. Find the area, the p-value, decide to reject or fail to reject, and then interpret. Now, I throw in this AP formula to show you the generalized version. Statistic is, in our case, the sample mean. The parameter is the claimed value. Standard deviation is the standard deviation divided by the square root of the sample size. Now, the formula is going to be slightly different when we get into T a little bit later, but for now, we're sticking with Z. So basically, the hypothesis test, how does a test question work? So basically, I like to really marry everything together. In other words, the confidence interval and the hypothesis test, I put it all together. So suppose a gas mileage of the hybrid Chevy Clunker is claimed to be 50 miles per gallon. Now, I would also throw in the phrase, you think it's lower. And the proper term is, I think, that for grammar. You think it may be lower. And the reason we have the alternative hypothesis is less than 50, number one, I'm saying you think it may be lower. Number two, the sample mean is actually lower than that. Now, point estimate, you would only have to do that if you are given, if it's a proportion or if you have sample data. The hypotheses, you will not have to verify the conditions. Conditions will be implied, so we will basically be skipping that step. We determine the test statistic to round that to a minimum of 3 decimals, and we find the critical value that determines our rejection region. And we determine the p-value, and based on the p-value and the critical value, you decide whether to reject or fail to reject the null. Now, it's kind of redundant because, yeah, you'll reject it or fail to reject it using both methods. But the other reason we do the critical value is margin of error for a confidence interval. Then you state the conclusion. That's kind of the big thing. Alpha level and hypothesis test, you do the confidence level, margin of error, interval, and then you interpret. So we're going to basically go through an example that came right from a test. So, okay, so what we're going to do here is this is an actual test question that I've asked in the past. So it is claimed that historically the average grade in general chemistry at the University of Texas is a 75. You have reason to suggest or believe that grades have been inflated and the mean should actually be higher than that. So we have a sample of 33 students showing a mean grade of 78.12, and historically you have a population standard deviation. So the hypotheses, the null and the alternative, we're dealing with means here, and 75 is going to be on the other end of this, and it has to be for the same thing. In other words, it's going to be on the same side. 75 is our question value, so to speak. And since we think it's higher and the sample mean being given to you is actually higher, the alternative is going to be greater than. Now the null, we could put less than or equal to, or that the null will simply be equal to 75. So you have the sample mean of 78.12, the population standard deviation of 6.54. You have a sample size of 33. So we're going to determine the test statistic, which is this here, x minus the mu over sigma over the square root of n. So we go about figuring that out real easily. 78.12 minus 75, and divide that by 6.54 over the square root of 33. So I'm also going to show you how to do these things directly in the calculator, but for now we're just going to kind of do it step by step, so to speak. So basically you would do 78.12 minus your 75, and then inside of here set up another fraction, 6.54 over top of square root of 33. And we are going to get a 2.7405, which we can call that 2.741. So 3 decimal places is always the rule of thumb for a standardized, for a test statistic here, 2.741. Now we also knew that it was going to be positive because the alternative showed greater than. So now we're going to do the p-value for this. So basically, this is obviously a right-tailed test, and this drawing's not the best looking thing in the world, but it'll do. So what you're going to do here is basically just normal CDF this from 2.741 to 10, and we get 0.0031. Now, that is obviously a low p-value. We are going to reject the null. So basically, I used to ask kind of E and F together, but we're going to reject the null. Now, even though we know that we're going to reject the null here, what I'm going to do here is determine the critical value. So keep this in mind. Alpha is 0.025. We're still dealing with large degrees of freedom here. So 0.025 and 1.96. And it's always helpful to make a little drawing here. So the critical value is going to be 1.96. Now, that is going to help us when we go to do our confidence interval. But the z-value that we got is inside the rejection region. Now, needless to say, we've rejected the null. And so how would we conclude this? What would we write in terms of a conclusion? Well, best way to go about something like this to kind of start you off with is based on our data, you should always open 33 students in general chemistry at UT. And here's the thing, we rejected the null. And by rejecting the null, we went with the alternative hypothesis. And since we went with the alternative hypothesis, we have evidence to suggest that the true population mean grade in general chemistry is actually higher than 75. Now, that is more than enough. I mean, that's enough for your answer. That's going to suffice. But this is kind of extra info. You do not need to, no need to really write this, but I want to indicate what that p-value means. The p-value of 0.00031 means that the probability that our group mean is at or above, what was the sample mean, 78.12, is 0.0031, given that the true mean grade is actually 75. The probability that, and we should say that we would get for our group mean, and this is probably not as grammatical nice as it probably would be, as Weird Al might call this. This is probably a word crime. But yeah, you don't need to write this, but that's what the p-value of 0.0031 is actually going to mean. So, now what is the corresponding confidence level based on alpha? Well, keep this in mind. Alpha was 0.025, and it was right-tailed or one-tailed. And believe it or not, this is actually very easy. Look at your little sheet here. 0.025, and it corresponds to 95% right there. So this is going to be a 95% confidence level. Now, that's going to come into play in a little while as well, especially when we do this all in the calculator. This is going to be a good thing. Now, if you remember, your margin of error is your critical z-value times standard deviation over square root of your sample. Now, the nice thing is we've already figured out the critical value, which was 1.96. You use the same exact thing as you did before. So let me go back to where I had this. So I kind of lost my spot here. So yeah, you'd have 1.96 times 6.54 over the square root of 33. And, rounding it to 2 decimal places. So if we figure this out here, so you do 1.96 times whatever this is, 6.54 over top of square root of 33. And we are going to get 2.23. So there's your margin of error of 2.23. I just want to make sure I have that right. That should be right. Yep. So now the confidence interval in and of itself is your sample mean plus or minus your margin of error, not the population mean plus or minus your margin of error. So basically you would take 78.12 plus or minus 2.23, and so that means you're going to get a low value and a high value. So you're going to go between 75.89 to 80.35. So that is going to be your confidence interval. Now, it can also be written as an interval, kind of like this. But I prefer it written in this format, and this should be a less than symbol, kind of a cruddy looking less than symbol here. And then to interpret the confidence interval, basically it's kind of like a hypothesis test based on a sample of 33 students in general chemistry. We are 95% confident that the interval between 75.89 and 80.35 captures the true population mean grade in general chemistry at University of Texas. So not a bad deal here. Now, one thing that you'll notice here, and you don't have to point this out, so this is kind of extra information. We remember that the alternative hypothesis was that the mean was above is greater than 75. So the entire confidence interval lies above 75. Remember, we rejected the null hypothesis. Now, that is what I like to call, again, extra information. But you're going to see that in just a few minutes when we do the calculator examples. Now, if you go to the next page, it explains how to do the testing and intervals in your calculator and on StatCrunch. So I'm going to go to a z-test here. Now we're going to input stats, and we're going to use 75 here. Now our population standard deviation was 6.54. Our sample mean was 78.12. And our sample size was 33. Now, in addition to that, our alternative hypothesis, if you remember, was greater than. So what I'm going to do here is kind of display this for you. Now, the cool thing is when we do the corresponding z interval, everything else is going to be in there for you. So we can calculate this or we can draw this. And here's what we've got here. if you look, this is all familiar. Your z value of 2.741, your p value of 0.0031. Now, if we go and do the z interval, not the t interval, but the z interval, you'll use stats. And since we did a 95% interval, we don't have to change anything here. So you're going to calculate this, and you will see, yeah, this does more decimal places, obviously, but they are the same thing. So that's going to make your life, I think, a little bit easier. Now, what's the purpose of, so yeah, confidence intervals and hypothesis tests. One thing we're going to do here is, these directions will show you how to do everything you need and on StatCrunch. Now, if you look at this example for 1A, 1B, and 1C, basically, a pit crew claims that its mean pit stop time for 4 new tires and fuel is less than 13 seconds, and a random selection gives you a sample mean, and the sample mean is going to change. That's going to be the only thing that changes in all these problems. But needless to say, since the sample mean is less than 13, and it says the mean pit stop time is claimed to be below 13, that's going to be your alternative. The null would be either greater than or equal to, or simply equal to 13. Now, instead of doing this all by hand, what we're going to do here is we're going to use the calculator to kind of verify everything. So we're going to go into z-test, and we have 13 seconds. The standard deviation is going to be 0.19. So the sample mean in this case is going to be 12.9219. Now you're probably thinking, why am I doing that? Well, trust me on that. And make that 32. And the alternative hypothesis is going to have to be less than here. So when you do that, I'm going to kind of post this here. Basically, again, for 1B and 1C, the only thing that's going to change on all three of these is that sample mean. That is the only thing that will change. Just the sample mean. So, what we're going to do here now is go ahead and carry this thing out. And this is what I like to call a very special case. Now, if you notice, you look at this p-value here. This p-value it's actually technically higher than the alpha value is, not by much, but this is what we call a very special case. I will never give you a case like this on a test. Rather, this is kind of the special case where the p-value is, we'll call this right on the money. I like to say right on the money, even though it is a little bit higher. I would not give you one like this on a test or anything. Now, if we go to the interval, everything is in here except we need to change that confidence level to 0.98. So we do that, and what we've got here is the interval goes between 12.844 and 13. In other words, this interval, here's our claim mean, and it's right on. So, in other words, what I'm hopefully going to impress upon you here is when the p-value is right on the cusp, like we see right here, so will the confidence interval. And rather than spend time actually calculating this by hand, I kind of decided it was a little bit easier to just do it this way using the calculator. So this was also more or less the basis of your third case study, or fourth case study, I should say, that you actually won't be needing to do now. So that case, yeah, the p-value is right on the money. And no, I will not actually ever really give you a case like that, ever. So what happens now is we're going to change that sample mean to a 12.8. So if we do a 12.8, that's the only thing that's going to change here. And what's going to happen here is we go to calculate this, and I probably made, well, that p-value is very small. Basically, with scientific notation, the p-value is 1.3 times 10 to the negative 9. Basically, or to 4 decimal places, you can just say 0. But needless to say, this was a reject the null case. Because if p is low, the hoe must go. Yeah. So then what we'll do is we're going to do the corresponding confidence interval. So we go to Z interval once again, and this time with everything. We see that the interval goes between 12.722 and 12.878. Now remember, the alternative hypothesis was less than, and this entire confidence interval is below 13. And the significance of 13 was, well, that's our clean mean. Our clean mean was a 13 for this. So what we'll do now is we'll do the last part of this where we'll change this to a sample mean of 12.95. So when we get 12.95, what we're going to get here is, I believe we're going to fail to reject the null. In that first part, it was a no decision. The second part, question B was reject the null. So you could probably guess by process of elimination, yeah, we are going to fail to reject the null here. So that's when, yeah, you will fail to reject the null in this case. Now, again, what it means to fail to reject the null is you just don't have enough evidence to believe that the population mean is higher or lower or whatever. And if we do the corresponding interval based on everything, we see that our confidence interval actually goes between 12.872 to 13.028. And the confidence interval does contain our 13. Now, you don't actually have to indicate that, but what I'm doing here basically is if you fail to reject the null, the corresponding confidence interval will contain the population mean, or the claim mean, I should say. Now, we're going to do the same thing for this is a two-sided test, and might I add, this is probably a poor example of a two-sided test. Because in the real world, we really want to go higher or lower. So, according to a study, the mean cost of bariatric or weight loss surgery is $21,500. You think it's different. So, this is going to be a two-sided test. So, how does this work as a two-sided test? Well, basically, the only thing we're going to be doing here is inputting stats. The claim mean was 21.5. Standard deviation was 2250. In this case, it was, what was the sample mean? 2618. And we had a sample size of 25. And what we're going to do here is it's going to be not equal to. So we carry out the hypothesis test like normal, and let's see what happens. And as you probably could have expected, this p-value, yeah, technically it's a little lower, but the p-value is exact, 0.05. I mean, come on, if you were writing this out, you would see that. Excuse me. All right, so if the p-value is right on the money, is the what about the confidence interval? Well, 95% confidence interval for this. So we do this. We have to change that level to 0.95. And I guess the good reason I kind of did this example like this is because it's dealing with money. The confidence interval is right on the money, just like the hypothesis test. So what you're going to do here, now, again, I would not give you one like this on a real test or anything, so don't freak out about that or nothing. So you kind of lucked out there. But what you see here is, 95% confidence. Now, how do we know this is a two-sided test? I mean, we know it's a two-sided test. So if you look for area in two tails of 0.05, that's going to correspond directly to 95%. Now, in the older days, I would actually have students do calculate the 90% and the 95%. But we're just going to kind of go straight up here. So this is what we would call a no decision. Now, we're going to see basically the only thing that changes in the rest of these problems is the sample mean. That's the only thing that's going to change. So if we do this, now we're going to make this sample mean 20,695. And you might be wondering, how do I do this? Where do I come up with this? And I'll show you that in a little bit. But we calculate this, and we see that the p-value is definitely higher than 0.05. So this is where we fail to reject the null. You're going to fail to reject the null in this case. Now, if we go to do the interval that goes with this, we see that the interval will contain the 21,500. Now, so basically, the confidence interval does contain the claimed value for the mean here. So not a bad deal, if I do say so myself. Now, for the last one, 20,195, and your guess is that you're going to be rejecting the null here, and you would be right. So 20,195, and 20,195. We carry this bad boy out, and the p-value is sufficiently low enough And since it's sufficiently low enough, you definitely reject your null here. And we go into the corresponding interval. We see that the confidence interval in of itself does not contain our claim mean. So that's what we've got for all this. Not bad, not a bad deal here. So now let me just show you here. I'm going to go to the Moodle page. So if you go to the Moodle page, here's what you're going to do here. If you go under class notes, Excel spreadsheet for you to use, it's labeled student sheet, and here's what you're going to do. You're going to go to z-test and intervals. Now, you have to edit, and here's the thing. You can, basically, you can only change what's in the green. You had 25 and 20,000. What was our, 20,195. Now, the one-sided alpha value, you would have to enter it as one-sided, so basically make that 0.025. Now, you do get the corresponding confidence interval that corresponds to 95%. Your margin of error is given, and you do get the p-value for the one and the two-sided test. Now, this works for t-test and intervals for stats, for data, and for proportions. You can change what's in the green. Don't try to change anything else, though. Now, what if we don't know the population standard deviation from earlier? Or, population standard deviation. We're going to use the t-distribution that we met, that we're going to learn right now. So, you might be thinking, oh my God, this is going to be kind of brutal here. It's really not, and here's why. It's basically a pseudo-normal type thing where basically you have your significance value, or alpha. You have your degrees of freedom, which is n minus 1. Degrees of freedom are the number of free choices left after a sample statistic is calculated. Basically, it's just whatever the sample size is minus 1. That's all. You don't have to do, there's nothing fancy, nothing brutal about that. It's what you're going to get here. So, with that in mind, what you can do, so basically, you can get your critical values when you have degrees of freedom. So we're not going to be looking at large anymore. Now, the mean, median, and mode of the t-distribution are equal to 0. The t-distribution is bell-shaped and symmetric. The total area under the t-curve is 1. Now, the tails in the t-distribution are thicker. So you might be wondering, well, what the heck is this? Well, here, basically, it's a parameter called the degrees of freedom. And if you look at this, the normal curve has the highest peak and the lowest tail. The t-distribution with the lowest degrees of freedom has a shorter peak and the highest tail. What happens here is, as the distribution increases, as the degrees of freedom increases, it becomes closer and closer to normal. So that's why when the degrees of freedom increases, it basically terminates at what we call the large. And think of it as an asymptote. If you've taken pre-calc, it cannot be any smaller than this. But the purpose of the t-distribution is it is going to give you a more conservative estimate, so to speak, and wider wiggle room. Now, if you go to Moodle here And I didn't include that here. Give me 30 seconds and I'll change that. Okay, so if you go to your Moodle page, t-distribution curve on Desmos. Now, this red curve is the normal distribution curve. Now, the cool thing is you can actually change the mean. You can slide that around, and we're going to take it back to 0. And what happens is you can actually change the standard deviation. But I'm not so worried so much about that. This t-distribution is your blue curve. Now, if you start it like at 2 degrees of freedom, look at how the tail is significantly higher. But as this increases, basically the tails get shorter, and as you can see, this curve gets closer and closer to the normal curve. So that's the main idea with this t-distribution curve. That's how that's going to work. Now, we can find, as degrees of freedom increase, the curve's peak gets higher. It's an inverse relationship between tail and peak. Now, we're going to use the tables to figure out our critical value. So, for example, if we wanted to find the critical value T sub C for 95% when the sample size is 15, you want to look for 14 degrees of freedom. So 95% confidence and 14 degrees of freedom, you get 2.145. Now, if you remember when you did your inverse norms, you would be able to do center. Now, kind of the bad thing is, middle 95%. Inverse T does not have the option. Now, if you entered each of these percentiles, you went to inverse T this. If you go to inverse T, you have to enter the area. There's no, and this is why we're going to be using the table from here on in. But you see negative 2.145 for that one. And if you inverse T 0.975, not log, but 0.975, it's going to paste at positive 2.145. Same thing. So that's what you're going to get for that one. Not a bad deal. But we're going to be using the chart. Much easier that way. So what will happen here is, what is the purpose of the t-distribution? Well, as I said, it gives you more wiggle room, so to speak. So wiggle room, the purpose of the wiggle room is, it's more conservative, so to speak. So if you look at this, the T, it does allow for more error. It came about, the t-distribution kind of came about where a quality control engineer for the Guinness Brewing Company actually found that using the Z distribution produced too many type 1 errors. In other words, they were throwing away too much good beer. So what's going to happen here basically is he found that doing the t-distribution gives more margin of error, a more conservative estimate. So basically, the interval corresponding to T will be a little bit wider as well. So your margin of error basically only changes to the critical T times standard deviation, sample standard deviation. Because we think about this in the real world, we do not know what the population standard deviation really is. So we're going to get a confidence interval. We're going to do the interval based on this. Now, what we want to do here is enter all this in the calculator, and hopefully I should have all this in there. So I'm going to do a 1var stat on this, and I'm going to have a sample mean of 306.32. Now, we'll do this for Z. We have a sample size of 20. I'm putting this in the middle because that's going to be the same value. And for T here. Now, we're going to use the population standard deviation for this, which is 35.29. For T, you would use the sample standard deviation, which is 36.21. Now, basically, your critical Z value, since this is 95% confidence, you just look for 95% confidence and go here, 1.96. Now, for the T distribution, it's not only going to, we look at 95%, you have to do 19 degrees of freedom. So this T value for 95% confidence is going to be 2.093. So in each event, we are going to determine the margin of error. And then we're going to go ahead and figure out the, and then we'll actually be coming back to this at another point, do the confidence interval. Now, if you do the margin of error here, which is your critical Z times this, 1.96 times 35.29 over the square root of 20, you're going to get something. Now, if you do the T distribution, it's your critical T times sample standard deviation over the square root of the sample, which is 2.093 times 36.21 over square root of 20. Even though it's 19 degrees of freedom, you still use the same sample size of 20. So if we calculate the margin of error in each event, we get 15.47 for this one. And when we do the margin of error for this one, we're going to get for the margin of error 16.95. So obviously the T distribution is going to give you more wiggle room, so to speak. So if we calculate this, didn't want to do that, but your sample mean plus or minus your margin of error, 306.32 plus or minus 15.47 and plus or minus 16.95. Yeah, minus 15.47. Yeah, 15.47 it should be. And we go from 290.85 to 321.79. And if we did this version of it, you're going to go from 289.37 to 323.37. So it's obvious that the interval for the t is actually going to be wider, which is a good thing. Now, believe it or not, you could actually do a z interval based on stats, or I mean on data. Now, the only thing is you do have to kind of override the standard deviation, and if you do the 95% confidence, we see that. Now, if you do the corresponding t interval with data, now if you chose stats, you would have to enter everything by hand, but it's just as well to use your data, and you would get what you see right here. So, not a bad deal. Now, we're going to come back to this at a little bit later. Now, what we're going to do here is we're going to look at finding, critical values. So, if we want to find the critical value t sub 0, or t sub c for a left-tailed test. Now, since it's left-tailed, t0, or I don't know why I should call this, it will be negative. And since our sample size is 21, the degree of freedom will be 20. So that's what you're going to get for that. So basically, look for area in one tail of 0.05 and 20 degrees of freedom. And by finding it, you get 1.725. But since it's left-tailed, it's going to be negative 1.725. Now, if you actually were to do, like if we called this area A, remember how we did normal CDF? You do TCDF from negative 10 to negative 1.725 and 20. The third parameter is going to be your degrees of freedom. So if you do that, so it doesn't ask you for a mean and standard deviation. It's just not going to work. And you do that, and we get pretty much 0.05. Now, so that's what you're going to get for that. And if you did, area B from negative 1.725 on, you would get 0.95. Now, if we maximize the TCDF at, say, 100, let's see if that might change it, or even 1,000. If you look, the difference really comes in a much later decimal place. So 10 is pretty much safe. But there might be a case where you get a t-value between like negative 10 and negative 20, or 10 and 20, and then you would want to use 100. So that's what you'd want to do in that event. So if we want to find the critical values here, this is a two-tailed test, so degrees of freedom is going to be 25 here. So alpha will be 0.10, and 25 degrees of freedom, it's going to be 1.708. And since it's two-tailed, you would do positive and negative 1.708. Now, the purpose of critical values, it's going to come back to us again when we get into the meat of the hypothesis testing. Now, assuming that neither software or calculator we're going to find, so here's what we're going to do. We're going to pick an arbitrary sample size of 19, and in a left-tailed test, we're going to do, say, negative 2.385. Now, here's what we're going to do. Obviously, this is a left-tailed test. So negative 2.385, we're going to find the exact p-value and since sample size is 19, your degree of freedom is going to be 18. So basically, you would do your TCDF from negative 10 to negative 2.385 with 18 degrees of freedom. Now, we're finding the exact p-value here, and that's how you're going to do this. The purpose of this exercise is to kind of show you how it used to be done, because 30 years ago, these calculators did not have TCDF. So we have a sample size of, well, degrees of freedom of 18, not 188, but 18. And we get 0.0141. Now, I like to call this before calculator. So, obviously, your table only has positives. So, look for t equal to 2.385, 18 degrees of freedom, and this is one tail. So you look at the one tail probability. So look at 18 degrees of freedom, and you'll want to find 2.385. Now you definitely won't. 2.385 is going to be between these two values here. It's going to be between the two values of 2.552 and 2.214. Now, what you really want to do with that is look at the areas in one tail that corresponds to that. 2.552 corresponds to 0.01. And 2.214 is going to correspond to 0.02. And so the area, or the p-value, is going to be between these two values. So I'll have to kind of stop this video here and just continue it at a later time.